Advanced force problems. These problems don't involve any new material or techniques. Instead, what makes them advanced is that they combine two or more pieces of previous problems: springs, friction, forces at an angle, forces on an incline, and kinematics from our previous unit. There's no single method to solving advanced problems, as each problem is unique and it may combine different aspects. I'll work through one example that combines friction and kinematics. A 2.4 kilogram book is given a push across a table with an initial speed of 1.5 meters per second. The coefficient of friction between the book and the table is 0.3. After being released, the book stops due to friction. How far will it travel after being released? Since the book comes to a stop due to friction, that means we will need to consider the forces acting on the book, particularly the force of friction. The question asks how far the book will travel. That sounds like a displacement, and we'll probably need to use kinematics. To consider the forces, we should start approaching this problem in the same way we did other force problems, with a force diagram and then a force table. Being on Earth, there will be a force of gravity down. From the picture, the book is moving to the right. Friction will oppose that motion and act to the left. Being on the table, there's likely a normal force acting up. Also, from our friction force equation, there actually can't be friction without a normal force. If Fn is 0, Ff will be 0. And it looks like we have unbalanced forces, which makes sense. The book is accelerating as it comes to a stop. Filling in those three forces in the force table, we can see the gravity and normal forces only act vertically, so they have 0 x component. Similarly, the force of friction only acts horizontally and has 0 y component. Since the book is only moving horizontally across the table, the y velocity is always 0. That means the net force is 0 in the y direction. The mass is given in the problem, so we can use that to find the force of gravity. M times G equals about 23.5 newtons, and negative since it's down. In order for the vertical forces to add to 0, the normal force then would be positive 23.5 newtons. The force of friction isn't given here. The coefficient of friction is, though, and we just calculated the normal force. We can then calculate the force of friction. 0.3 times 23.5 equals about 7.05 newtons. Looking at the force diagram, I know it needs to be negative since friction acts to the left. And with all the x components filled in, I can find the net force in the x direction would be negative 7.05 newtons. Before we can use kinematics, we need to know what the acceleration is. And Newton's second law can help us with that. Net force equals mass times acceleration. The negative net force told us it was to the left, so the negative acceleration tells us that the acceleration is going to be to the left. Throwing it back to our kinematics unit, let's identify our variables. A equals negative 2.94. The initial velocity was 1.5 meters per second. It's positive since that's moving to the right. The final velocity was 0 since it comes to a stop. And I'm trying to find what the displacement is. There is no time information, and the equation that relates these four variables is plugging in the variables. The displacement is 0.383 meters. It came out positive, meaning the book slid to the right 0.383 meters, or about 38 centimeters before coming to our stop. And that's our final answer. Keep in mind that each problem may be different, so stay on your toes and keep in mind all we learned this year.